So in today's video, we're going to look at 7.3 and 7.4. Both of these are types of discrete distribution. First one we're going to look at is the uniform distribution, and the second one is the binomial distribution. 7.3 is a really short chapter. There's not much to say about the discrete uniform distribution. The big thing to make note of here is the word uniform, okay? Whenever you see the discrete uniform distribution, it means that every single outcome has the same probability, okay? It's as simple as it gets. So every outcome, whenever you do an experiment, every outcome has the same probability. Okay, classic example of this, rolling a die. Okay, each one of those outcomes, 1, 2, 3, 4, 5, and 6, each one of those has a probability of occurring of 1 over 6, okay, 1/6. So every outcome has the same probability. Same when you toss a coin, okay? When you flip a coin, you're either going to get heads or tails. Each one of those outcomes has a probability of 1/2 of happening. Same if you pick any one card out of a deck of cards. Each card has a probability of 1 out of 52, 1 over 52, of being picked. Okay, so every outcome has the same probability. You don't tend to find it a lot in most of the things that we're going to be looking at. But the good thing about a uniform distribution, apart from using it in terms of dice and coins and cards, the good thing about it is if you are doing a certain experiment and you know absolutely nothing about what the outcome is going to be, if you need an estimate of what you think each of the probabilities of the outcomes is going to be, a uniform distribution is a great place to start, because you can say, okay, I'm doing this experiment. There are 4 outcomes in this experiment. I have no idea which one of my outcomes is most likely. I don't know which one's least likely. I have no idea how this is going to turn out. I've got no historical data to tell me how this is going to turn out. So I literally have no clue. Well, what I can say is, okay, I've got 4 outcomes. I'm going to assume, just to start off with, I think that each outcome has an equal chance of happening, a 1 in 4 chance of happening. So I can say, okay, each one of my 4 outcomes has a 1 over 4 chance. Okay, so it's a good place to kind of start as a guess of where you think your experiment might go. And then once you have some experimental data, once you have some historical data, you can clearly say, okay, it's not the uniform distribution that I thought it was at the start. Now I have some more stuff to go off of. I know that the actual probability is this. Okay, but it is a good place to start if you literally have no idea what the probability of each of your outcomes in a certain experiment is going to be. But the main time that we use the uniform distribution is rolling die, when we flip a coin, and when we pick a card out of a deck of cards. That's the main time that you see it. Okay, next we have 7.4. This is going to round out chapter 7 for us. And it's the binomial distribution. This is the first, more complex distribution that you're going to see. There's a great video on this. Again, it's one of the Against All Odds videos, and you can find it on that tab on the Blackboard page. So go ahead to the Against All Odds tab, and there is a video about halfway down called Binomial, so you can go ahead and watch that. The binomial distribution. Whenever you run an experiment, it is a binomial experiment if it has 5 certain properties. So we're going to list those properties. So a binomial experiment okay. Well, first off, and this isn't one of our 5 things, but first of all, it's random. Okay, we have no idea what's going to happen. Okay, it's a discrete random variable. So we know that we're going to be dealing with something that's countable because it's discrete, and we know that this thing is completely random, so we don't know what the outcome is going to be. That's the main thing to start with. The 5 things that you need to remember. Number 1, there are exactly 2 outcomes at each trial. Okay, there are 2 outcomes at each trial. There are no more than 2, there are no less than 2. Okay, we tend to call those 2 outcomes success and failure. Success is the thing you want, failure is the thing you don't want. Okay, so even if like a particular problem doesn't exactly say, hey, success or failure, like we are looking at the probability of success in this, we are looking at the probability of failure in this. You don't necessarily need to see those words, but success is the thing that you want and the thing that you are looking for. Failure is the thing that you're not looking for. So you've got success and failure. Okay, for example, I might be trying to look at the number of times I get heads in 3 tosses of a coin. Okay, heads is my success because it's the thing that I am looking for. So I'm looking at the number of successes, the number of heads that I get out of my 3 tosses of a coin. My failure would be tails because it's the thing that I'm not looking for. So each time I flip the coin and get tails, that would be considered a failure because I'm not getting the thing I'm looking for. So that's one of the examples where it's not explicitly labelled success and failure, but you've got exactly 2 outcomes. One is success, one is failure. So, next thing, the experiment has n identical trials. Okay. N is the number of times you conduct the experiment. It's the number of trials within the experiment. So it's the number of tosses of a coin. It's the number of times you pick a card. It's the number of times you roll the die. Okay. And each trial is identical. So I'm not in one trial, I'm flipping 2 coins, and in the next trial, I'm only flipping 1. Okay, I'm doing the exact same thing each time, and I'm doing it n times. Number 3, the probability of success is P. Okay, so the probability that I get a success in each trial is labelled as P, and it is the same at every trial. So going back to what I just said, flipping a coin, you could say, okay, I'm looking for heads. I want to see the number of heads I get when I flip a coin. Heads is my success, tails would be my failure. The probability of success, the probability of getting heads, is 1/2. And it stays at 1/2 the entire time through the experiment. Okay, the probability of getting heads never changes. So the probability of success is P, and it remains the same in every trial. Number 4, this is a simple one. The trials are independent. They don't depend on one another. So what happened in one trial, so what I got on one toss of a coin the first time doesn't affect when I toss the coin the next time. Okay, the trials are independent. They don't affect one another. What I got on the previous trial doesn't affect what I get on the next trial. And finally, the binomial random variable is the count of the number of successes. So let's say I'm flipping a coin 5 times and I want to see how many heads I get. Okay, I'm flipping a coin 5 times, meaning that I have 5 trials, and I'm looking for the number of heads I get. So heads is my success. So my binomial random variable, my outcomes is what I'm saying here. My outcomes would be my number of successes. Now, if I'm flipping a coin 5 times, I can get at most 5 heads. I can get at most 5 successes. Okay, so I can get anywhere between 0 successes and 5 successes, because I can get anywhere between 0 heads and 5 heads in that experiment. Okay, so my possible outcomes are my possible number of successes. So we've been talking about how tossing a coin is an example of a binomial experiment. Let's now look at tossing a coin 3 times. Let's see if it satisfies these 5 points. Okay, so I'm tossing a coin 3 times and I'm looking at the number of heads that I get when I toss a coin 3 times. Well, each time I do this, I either get heads or I don't get heads. Okay, if I get tails, it's not heads. So I have exactly 2 outcomes: success and failure, heads and not heads. The experiment has n identical trials. Okay, so the experiment has 3 tosses of a coin, and each time I toss the coin, it's a new trial and it's identical to the last one. So I know that the first 2 are correct. The next one, the probability of success, the probability of getting heads, is 1/2. So I know it remains the same through every single one of my trials, through all 3 tosses of the coin. So I know that the probability of success remains the same. The trials are independent. First time I toss the coin is independent of the second time I toss the coin, which is independent of the third time I toss the coin. So each of the trials is independent. And the number of heads that I get, the number of successes I get, is going to be the possible outcomes. So I can get, in 3 tosses of a coin, I can get no heads, 1 head, 2 heads, or 3 heads. So I can get no successes, 1 success, 2 successes, or 3 successes. So they are my possible outcomes. So these 5 things are satisfied. I can come up with these 5 things for this particular experiment of tossing a coin 3 times. Therefore, it's a binomial experiment and can be given by the binomial distribution. It models the binomial distribution. So if we want to look at probabilities within a binomial distribution, within one of these binomial random variables, and I want to find what is the probability of a certain number of successes, okay? So for example, what's the probability that I get 2 heads out of 3 tosses of a coin, okay? Well, there is actually a mathematical way of doing this, and it is an awful looking formula, but we're going to quickly talk about it. And this is what your calculator is going to be doing, because it will calculate it for you. But I want you to actually see the formula. So I'll write it down and then we can talk about it. Okay, so I am looking at the probability that x is equal to little x. What that means is I'm looking at the probability of having x number of successes. So all this means here is the probability of having x successes. So for example, what's the probability of getting 2 heads out of 3 tosses of the coin? What is the probability of getting 4 heads out of 7 tosses of a coin? Okay, it's the probability of having x number of successes, whatever x may be. So in order to calculate that, it's this long formula here that looks complicated, but I promise it's not as bad as it looks. We'll start with this part here. P to the power x. P is just the probability of success. So in the example we've been looking at, where heads is the success, the probability of success is 1/2. And I take 1/2 to the power of the number of successes that I am looking for the probability of. Okay, so let's say I'm looking for the probability of having 2 heads out of 3 tosses of a coin. So I'm looking at the probability of having 2 successes. So I would take 1/2 to the power 2. Then this part here is 1 minus P. Now if you think about it, if P is the probability of success, and I only have 2 outcomes, either success or failure, the probability that I fail is 1 minus the probability that I succeed, because I can only either succeed or fail in any one of these trials because I've only got 2 outcomes. So 1 minus P is actually the probability of failing. Okay, and I'm taking that probability, 1 minus P, to the power of n minus x. Well, if n is the number of trials, so the number of tosses of a coin, let's say, and x is the number of successes I'm looking for, n minus x must be the number of times that I fail in this particular experiment, because I'm saying, okay, I want to look at the probability that I succeed x times. Well, if I succeed x times, I must fail n minus x times because I've only got n trials. So n minus x would be the number of failures in your particular experiment. So I'm taking the probability of success to the power of the number of successes multiplied by the probability of failing to the power of the number of failures. And finally, we need to look at this part of the equation. So C and X, all this means is it's the number of ways that I can have X things out of N. So I'm looking at the number of ways that I can have X number of successes out of N trials. So C and X is actually found by using factorials. The actual definition of it, and we'll talk about factorials as well. Okay, is n factorial over x factorial multiplied by n minus x factorial. By the way, your calculator will do all of this, so don't panic too much. I just want you to see what your calculator is actually doing. Factorial is where you take that value and you multiply it by every value that goes before it down to 1. So for example, 4 factorial would be 4 times 3 times 2 times 1. Okay, so it would be 24. So I'm going to take n factorial, the number of trials factorial, over the number of successes that I'm looking at factorial, multiplied by n minus x, the number of failures factorial. What this will tell me is it's the number of ways that I can combine X successes within N trials. So it's the number of combinations, the number of ways that I can get those X number of successes within the N number of trials. It's the number of ways, for example, that I can flip a coin and get 3 heads out of 4 flips of a coin. Okay, it will tell me the number of ways that I can do that. So it will tell me that I can do it a certain number of ways, and I can get like heads, tails, heads, heads. That will be one of my combinations. Heads, heads, tails, heads. That's another one of my combinations, and it will count how many of those that you can do. Okay, so it's just the number of combinations, the number of ways that I can get X successes within my N trials, and it will figure out all the combinations and tell you how many of them there are. So that is what your calculator is going to be doing. So when you go ahead and you try and find the probability that you have X number of successes out of N number of trials, your calculator is going to be using this formula. We're going to do one by hand just so you can see it. And then from there on out, I'm going to show you how to do it on your calculator because it's much easier. So let's say, and I've spoken about this before, let's say we want the probability of getting 3 heads out of 4 tosses of a coin. Okay, so I'm looking at the probability of 3 successes. Okay, heads is equal to success, and tails, which is not heads, would be failure. So I'm looking at the probability of having 3 successes. So I'm looking at the probability that X is equal to 3, the probability of 3 successes. Okay, we're going to our formula here. Okay, the probability of 3 successes. I'm tossing my coin 4 times. So I've got 4 trials. N is equal to 4, X would be equal to 3. Okay, I've got 4 trials, so N is 4. The number of successes that I'm looking at here is 3. So I would have 4 choose 3. Okay, so that would be 4 factorial divided by 3 factorial multiplied by 4 minus 3 factorial. Okay, again, we'll do that in a calculator in a second. Then I've got my probability of success. Well, the probability of success is the probability of getting heads, which is 1/2. And then I'm taking that to the power of the number of successes that I want. So I've got 1/2 cubed. And finally, 1 minus the probability of success, which is 1 minus 1/2, is 1/2, which makes sense because that's the probability of getting tails, which is my failure. So I've got 1/2 is the probability of failure to the power of the number of trials minus the number of successes. Okay, well, if I'm tossing a coin 4 times and I'm looking at the probability of having 3 successes, I've got 3 successes out of 4, which means I'm going to have 1 failure. So I'm going to have 1/2 to the power 1. So all I've done here is I've said N is equal to 4, X is equal to 3, and P is equal to 1/2. And I've plugged all of that in. Okay. So this part here we said was 4 factorial over 3 factorial multiplied by 4 minus 3 factorial. So then I'm going to have 1/2 cubed, which is 1 over 8. And I've got 1/2 to the power 1, which is just 1/2. This part here, okay, 4 minus 3 is just 1. 1 factorial. I'm multiplying 1 by everything that goes before it down to 1. Well, 1 factorial, therefore, is just 1. So this thing just cancels to 1. 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. So I can cancel the 3's, I can cancel the 2's, I can cancel the 1's. So this formula here actually just cancels to 4. So I've got 4 multiplied by 1 over 8 multiplied by 1/2, which is going to give me 4 over 16, which is 1 over 4, which is 0.25. So the probability of getting 3 heads out of 4 tosses of a coin, the probability of having 3 successes out of 4 trials is 0.25. Okay, you can do that for any number. You could do the probability of having 2 heads out of 4 tosses of a coin. You could do any number you wanted. Okay. What it may then ask you is something along the lines of, well, what is the probability of having at least 3 heads? So it could say to you, what's the probability that x is greater than or equal to 3? That would be the probability of having at least 3 heads, at least 3 successes. Well, again, we're in a discrete distribution here. I can't have a decimal number of successes. I either have 3 successes, 4 successes, that's it, okay? I can't have a decimal number of successes. So if I'm looking at the probability of having at least 3 successes in this case, I've only got 4 trials. I'm only tossing the coin 4 times. So I can get 3 heads or I can get 4 heads. I can't get more than 4 heads if I'm only tossing the coin 4 times. So the probability of getting at least 3 heads would be the probability of getting 3 heads plus the probability of getting 4 heads. So what you could do is say, okay, well, we figured out this probability was equal to 0.25. That's what we just figured out. And then you could go ahead and do this exact same formula again, but now you would be plugging in x is equal to 4. So I would have the probability that x is equal to 4 here. Then I would have a 4 here in place of the 3. I would have a 4 here. And then where the 1 is here, well, that was n minus x. N is 4 and x is 4. So I would actually have this to the power 0, which is 1. Anything to the power 0 is 1. So you could go ahead and figure this out instead with x is equal to 4. And if you did that, it comes out to 0.0625. Go ahead and plug in x is equal to 4 into that formula. Your n is still 4, your p is still 1/2. It's just x is now equal to 4, and you should end up with 0.0625. Adding those together, you would get 0.3125. Okay, so that is the probability of getting at least 3 heads. How about the probability now of getting less than 3 heads? A couple of ways you could do this, okay? I've just figured out the probability of getting at least 3 heads, and now I'm looking at the probability of getting less than 3 heads, okay? Well, another way of writing that would be 1 minus the probability of getting at least 3 heads, okay? If I'm looking at the probability that x is less than 3, that's the same thing as saying the probability that x is less than or equal to 2. Again, we're in a discrete distribution. If x is less than 3, I can't have a decimal value. So the next number that is less than 3 is 2. The largest number I can be at, the largest number of successes I can have is 2. So another way of writing this is the probability that x is no more than 2. It's less than or equal to 2. Well, if I'm looking at the probability that x is less than or equal to 2, that's equal to the probability that x is equal to 0, x is equal to 1, plus x is equal to 2. Okay? because I can't have any less than 0 successes. I can't have a negative number of successes. So I can have 0 successes, I can have 1 success, and I can have 2 successes. So if I add those together, that's the same thing. The only number of successes I can have is 0, 1, 2, 3, or 4. I can't have more than 4 successes or less than 0 successes in this case if I'm doing 4 tosses of a coin and looking at the number of heads. So I know that the probability of having 0 heads plus the probability of having 1 head plus the probability of having 2 heads plus the probability of having 3 heads plus the probability of having 4 heads should equal 1. I've got to land on 0, 1, 2, 3 or 4 heads. I can't have anything outside of that. So adding all of those together must be 1. So if I do this plus this plus this plus this plus this, I should get 1. Therefore, if I'm looking for the probability that x is less than 3, I said that that was equal to these added together, which must be 1 minus these two things added together. So it's 1 minus the probability that x is greater than or equal to 3. So always think of it in terms of a number line and look at the number of outcomes that you have. Look at your possible outcomes. Then you can see whether you have a less than or equal to, a greater than or or equal to, and you can figure out what numbers fall within that range. I'm going to show you a way of doing some of this on a calculator where you do have these inequalities, and that should help you not have to do this by hand. But as I said, use a calculator where you can, because this formula is not easy. So use the calculator. You're going to be using something called binomial PDF and binomial CDF, and it will solve all of these problems for you. You just have to remember, depending on whether it's looking at less than or equal to, or greater than or equal to, or less than or greater than, you may have to rewrite this in some way like I have done here, like where I've rewritten probability that x is less than 3. Well, maybe I could write that as the probability that x is less than or equal to 2. Okay, you may have to do some rewriting here in order to use your calculator, but once you have rewritten it, a calculator is a great tool. So how do we figure out those binomial probabilities more easily on a calculator? Well, there is a button on your calculator that will deal with all the different distributions that we're going to be looking at throughout this course. And the way that you find those is to go to second, and then this button here that says vars, you should see above it in blue is distribution. You're going to click on that. Now we're going to be dealing with a lot of these later on, but if you scroll all the way down, you should see options A and B are binomial PDF and binomial CDF. We're going to be using both of those today. Let's start with binomial PDF and what that means. Okay. If you have a TI-83 or you have one of the older 84 models, you are going to be putting in this information in the same order that we are on the home screen, just with commas between them. So make sure that you put it in the same order. It's going to go trials, P, X value. When you get to this, trials is the number of trials. So let's say we're doing our example, we're flipping a coin 4 times and we want to see the probability of getting exactly 3 heads. Now we know that the probability is 0.25 from what we've just done by hand. But let's see what the calculator does. So we have 4 trials because we're flipping the coin 4 times. The probability of success, that's the probability of getting heads in our situation, which is 0.5. And the X value, that is the X value that you are looking for, the probability that X is equal to this value. So we want the probability that X is equal to 3, the probability that we get exactly 3 heads. And then if you run that, you should get 0.25. So if you are looking for the probability that you have exactly this amount of successes, you are going to use binomial PDF. So if you want just the probability that X is equal to something, this is what you use. As I said, if you've got one of the older calculators, when it comes up with this on the home screen, you are just going to do 4, 0.5, 3, close parentheses.
So just put it in that same order: trials, probability, and then the number of successes that you are looking for. Let's go back to that menu and go into binomial CDF. Comes up with the same menu, but this does a slightly different calculation. What this does, and it is very useful, it's just sometimes you have to kind of do some calculations yourself beforehand. This deals with what the probability of having x less than or equal to this x value that you put in. So this will always calculate the probability that x is less than or equal to this value you put in. Now, sometimes you'll get a problem where it says, okay, what's the probability that x is greater than this value? What's the probability that x is greater than or equal to this value? And we looked at that when we did this by hand. Well, when you do that, you will have to transform a greater than or equal to into 1 minus a less than or equal to. Then you can figure out the probability that x is less than or equal to this value, do 1 minus that value, and then you will get the answer that you are looking for. Okay? So let's say, I'm going to do a couple of different examples here. Let's say you want the probability that x is less than or equal to 2. I want the probability of getting at most 2 heads. Well, that means, again, my number of trials is 4. I'm looking at flipping the coin 4 times. Probability of success, the probability of getting heads is 0.5. And I want the probability that x is less than or equal to 2. So 2 goes in there. So what this will do is calculate the probability that x is equal to 0, that I have no heads, the probability that I have 1 head, and the probability that I have 2 heads, and add those together. And then you calculate. And we get 0.6875. Now remember, the probability that x is less than or equal to 2 in a discrete distribution is the same thing as saying the probability that x is strictly less than 3. Okay, we looked at that in our last example. So there are many different ways of writing this, but make sure that the value that you put in for your x value is the less than or equal to outcome. Okay, so if it says the probability that x is less than 3, well, if it's less than 3, it's less than or equal to 2. Okay, now, if I wanted, I've just figured out the probability that x is less than or equal to 2. If I want the probability that x is greater than or equal to 3, okay? Now, we said this in the last example as well. The probability that x is greater than or equal to 3 is 1 minus the probability that x is less than or equal to 2. So I know that the probability that x is greater than or equal to 3 includes the outcomes 3 and the probability of the outcome 4. Okay? So by doing 1 minus this, I would figure out the probability of those two things happening. So if I did 1 minus, and then I can do second and answer, this would be the probability that x is greater than or equal to 3, and this is the probability that x is less than or equal to 2. So sometimes, binomial CDF is great, and all you have to do is just plug the number in if you have a less than or equal to. But sometimes you're going to have to deal with a less than, in which case you're going to have to come one number further down so that you've got a less than or equal to. Sometimes you're going to have a greater than or a greater than or equal to, when you're going to have to kind of figure it out and then do a 1 minus that value. Okay, so it is a very, very useful tool. Just remember, binomial PDF is if you are looking for an exact outcome, the probability of an exact outcome happening. Binomial CDF, okay, the C meaning cumulative, means that we are looking at for the probability that x is less than or equal to that x value, to that outcome. Okay.
So our next question is going to be, what is the shape of the binomial distribution? What does this thing look like if we go to graph it? Okay. The answer is it all depends on the value of P. It depends on whether you have a large probability of success or a small probability of success. Okay. Let's say that P is small. Okay. For example, let's say that P is 0.1. Okay, so we've got a small probability of success. Okay, the probability that we're going to succeed in any one trial is pretty small. It's only 0.1. We've only got a 10% chance of succeeding here. Okay, in that case, the distribution is skewed right. Remember, when we say that something is skewed right, it means that it has a tail to the right and the majority of the data is to the left. So let's go ahead and draw that out of what that would look like on a graph. Okay, I'm plotting the x value, okay, the number of successes against the probability of that number of successes. So I'm plotting the number of successes against the probability that we will have that number of successes out of n trials. Okay. Well, if it's skewed right, it means it's got a tail to the right, which means it's got the majority of its data to the left. So why does the graph take on this shape? Well, remember, we're looking at a particular situation where the probability of success is small. Okay, in this case, we're just looking, let's say, a probability of 0.1. Okay, that's the chance of having a success in any one trial. Well, let's look at having a large number of successes. So out of my n trials, I've got a very large number of successes out of those n trials. So it's like having 9 successes out of 10 trials. Okay, I've got a large number of successes. Well, the probability of having a large number of successes is very small because my probability is down here. Okay, it flattens out and it's very, very small. So the probability of having a large number of successes is small. Well, that makes sense. If your probability of success in any one trial is tiny, the probability of having a large number of successes is incredibly small. Okay, if you've only got a 10% chance, in this case, your probability is 0.1, you've got a 10% chance of succeeding in any one trial. Well, in that case, your probability of having 9 successes out of 10 trials is incredibly small because you've only got a chance of succeeding of 10% in any one trial. So that side of the graph makes sense. Now let's look at the other side. If I have a very small number of successes out of my n trials, so I'm looking at like maybe 2 or 3 successes out of 10 trials, well, I've got a much higher probability of that being the case when I've got a small probability of success in any one trial. That's why my probability is up here. Okay, if I've only got like a 10% chance, a 20% chance of succeeding in any one trial, so my probability of success is like 0.1 or 0.2, I'm much more likely to have like 2 or 3 successes out of my 10 trials than I am to have 9 successes out of my 10 trials. So that is why my probability is so high when my number of successes is small and so low when my number of successes is large. Okay, so this is when P is small. Your probability of success is small. When the probability of success is large, you can imagine the opposite is going to happen. So let's say in this case, P is equal to 0.8. Okay, I have a large probability of success. I've got an 80% chance of succeeding in any one trial. I've only got a 20% chance of failing. Then my distribution is skewed left. So if it's skewed left, it means that I've got a tail to the left and the majority of my data to the right. So again, I'm going to plot my number of successes, X, against the probability of having that number of successes. And it is skewed left, which means I've got the majority of my data to the right. Again, let's think about it in terms of the probability of success. If I've got a high probability of succeeding in any one of my trials, okay, I've got an 80% chance of succeeding here, the probability that I will have a large number of successes out of my end trials is much more likely. Okay, if I've got a probability of success in any one trial of 0.8, I'm most likely, let's say I've got 20 trials, I'm going to have a fair amount of successes out of my 20 trials if I've got an 80% chance of succeeding in any one trial. Okay, I'm probably going to have 16, 17, 18 successes out of my 20 trials. That's much more likely. So I have a high probability of succeeding in any one trial. So I have a high probability of having a larger number of successes. In the opposite way, okay, if I've got a high chance of succeeding in any one trial, it's very unlikely that I'm only going to have 2 or 3 successes out of 20 trials, okay? I have a much lower probability of having a low number of successes when I have a high probability of succeeding in any one trial. So that's why it's so low down here. So it's the opposite for each one. It's skewed depending on what your probability of success in any one trial is. Couple more things that you need to know, and you need to remember these. They're not that difficult to calculate. They're actually super simple. Is the expected value and the variance, and hence the standard deviation of a binomial random variable. The expected value, you can kind of figure out why this is the formula for it. The variance, you just kind of have to remember. You don't need to know where it comes from. It actually has some calculus behind it, so don't worry about that. The expected value, okay, my expected number of successes. On average, okay. My expected value of a binomial random variable, this only works for binomial distribution, is the number of trials times the probability of success, okay? Again, we always call our expected value the mean, okay? It's the average number of successes that I expect to have, okay? It's the expected number of successes. Why does this make sense? Well, I've got the number of trials multiplied by the probability of success. Let's say I've got 10 trials, and the probability of succeeding in any one trial is 0.5, okay? So let's say I've got 10 trials and my probability of success in any one of those trials is 0.5, okay? Well, you would think if my probability of success is 0.5, okay, I have half of the time I'm going to succeed, half of the time I'm going to fail. You would think that your expected number of successes is probably going to be 5, okay? If you're succeeding half the time and failing half the time, you'd think, okay, well, I'm going to succeed in half of my 10 trials. So I'm going to expect that I'm going to succeed 5 times out of 10. That would make sense. In order to do that, I've just done n multiplied by the probability of success. That's where this comes from. Okay, I take my number of trials multiplied by my probability of success in any one of those trials, and it should tell me the expected number of successes that I would expect to have. Okay. And the next thing you need to know is the variance. Now this one, as I said, you don't need to know where this formula comes from. You just need to remember it. And this only, again, works for binomial. This formula does not work for any other distribution. Okay? I'm taking, it's actually the mean, that expected value that I just looked at, n times p. And then I'm multiplying that by the probability of failure, 1 minus p. That is my variance of my binomial distribution. If I want the standard deviation of my binomial distribution, as always, it is just the square root of my variance. So it would just be sigma, and it is the square root of this. So it's the square root of np times 1 minus p. So if you know the number of trials you're looking at and the probability of success in any one of those trials, then you can go ahead and figure out your expected value, your variance, and your standard deviation. Okay. All you would have to do, just as a quick heads up, so let's say again, if I've got n is 10 and my probability of success is 0.5, so let's say I'm looking at 10 tosses of a coin and I'm looking at the number of heads that I would get. The probability of success, the probability of getting heads in any one of those 10 tosses of the coin is 0.5. So to figure out the variance, I would do 10 multiplied by 0.5, and then 1 minus p is 1 minus 0.5, which is actually also 0.5. So I would have 10 multiplied by 0.5 multiplied by 0.5. That would be 10 multiplied by 0.25, which would be 2.5. If I then wanted my standard deviation, you'd have to plug this into a calculator. It would just be the square root of that number. Okay. So hopefully this isn't too difficult. You just have to be able to realize when you are looking at a binomial experiment. The main thing is it has two outcomes. Okay, it only has those two outcomes, success and failure. After that, you can figure out the number of trials. You can figure out the probability of success. You can figure out the number of successes that you are looking for. You can figure out the probability of that number of successes that you are looking for. You can figure out the probability of having at least a certain number of successes or less than a certain number of successes, as we did on the calculator. And then you can figure out what is my expected number of successes, what is my variance, and what is my standard deviation of this random variable. Okay. Go ahead and try, you can do the 7.3 and 7.4 homework now. Go ahead and try those and let me know if you have any questions. This can kind of take a second to wrap your head around to make sure that you know that you are looking at a binomial distribution. But if you need any help with it, let me know, and I will see you in the next video.